Okay. So there are two pictures that are on the Blowgun Lab. One picture looks something very similar to this, although they have a very well-drawn picture of a person blowing the blowgun. But the essential stuff is right here. And then there's a second picture that shows you the guiding questions for the lab. I'm just going to go over the physics of the lab and sort of just generally how do we get our answers for this lab. And then I'll stop the video and then just demonstrate for the students that are here today. Okay. So what we're going to be doing is we're going to be shooting blowguns horizontally. This is the key. It has to be a horizontal shot. Horizontally, and those darts are going to embed themselves in a target on the other side of the room. And just like in problem 6, we're going to try to figure out what is the velocity of the dart. In problem 6, you're trying to figure out how fast the bullet was going. Here, we're going to figure out how fast the dart was going. And we can do that just with a couple measurements. We don't have to have a stopwatch or lasers or anything like that. All we need are just meter stick measurements, distances. So how does it work? Well, the first thing is that we're going to have to measure the height of where we shoot these from. And in the room, we have lab tables set up, so you're going to have to measure the height of the initial height, so dy initial. Those things will travel, those darts will travel across the room until they stick into a target, so we'll call that dy final. So final heights, and so stick at some initial final height. And of course, that's going to be below your initial height. Remember, this was, if the thing just perfectly went straight across, it would go all the way across to the initial height again. But so here's the initial height it was shot from, and it's going to drop this far. If you want to figure out the velocity, the very first thing we have to do is figure out how long it's in the air. And it was just like the previous problem that we solved. How long is it in the air is really a function of how far does it fall, right? How far does it fall? In the bullet problem number 6, it fell all the way to the ground, and so all we needed, it fell the initial height. Here, the dart is going to stick into a target, so it's not just as simple as saying, oh, the dart falls the complete height that it's launched from. It falls some smaller height. It falls from here to here, right? That's the distance it falls. So to calculate this distance, you would have to go dy initial minus dy final. Dy initial is the height of the lab table that you shoot it from. Dy final is the height that it sticks into the target. And whatever the distance is, or the difference between these two distances is how far it falls. Okay. So first things first, try to figure out how long it's in the air. So that is a y direction question. So there we go. Let me just do that in red. And it's going to be, we're going to treat this just like the previous problem we did, where, let's do it right here. dfy equals diy plus viyt plus 1/2 gt squared. Again, because in the y direction, the initial velocity is downward, or like, let me rephrase it. In the y direction, because its initial motion starts downward, I'm going to call downward positive, upward negative, and it just assures that I have positive values. You could always say positive is up if you want to, and you would end up with 2 negatives in your calculation, which would cancel out anyway. So you can do it either way. Anyways, this is the way I'm doing it. So we're trying to solve for time. So the way we're going to get this is that the let me phrase it. dfy minus diy is, now the initial velocity, remember when it falls, is 0. And that is going to equal 1/2 gt squared. So in this case here, you're going to have, we're solving for time. So it's going to be 2 times dfy minus diy all over g equals t squared. So if you want to figure out what t is, you're going to take 2 times the falling distance. Remember, this is going to be your falling distance. And yes, it's going to be a negative sign. That's okay. We can swap. We can switch it. Just a real quick aside. On my reference frame, this is actually going to be dyf minus dyi. I want to point out that it doesn't matter. 2 minus 6 is -4. 6 minus 2 is +4. You can just, the answer is 4. So in this case, it doesn't really matter, but according to my reference frame, just to be super technically correct so we don't get a lot of email questions, on this reference frame, this is really the way it would look. So I'm just going to do a quick change here. Again, it doesn't affect the physics, not one bit. So this would be, again, does not affect the numbers, does not affect the physics. It would just mean that you would have to cancel out a negative sign manually. Anyways, so we'll be able to get the time this way. So if this thing falls, you know, for example, if this thing was 1 meter high and it hit here at 0.2 meters, that means it must have fallen 0.8. So you go 2 times 0.8 divided by 9.8, take the square root, and that's your time. Okay, that will get you the time that's in the air. That does not solve the velocity yet, but you know that it has that amount of time to get from here to here. And so again, just like in problem 6, we're trying to figure out Vx, right? So we would say that dx equals Vxt. As I showed in the previous problem, there's no acceleration term, so that term goes away. In the x direction, the initial position is 0, so that term goes away. All you're left with really is d equals Vt in the x direction. So dx all over t equals Vx, which is the point of this lab, is to figure out this x velocity. So if you get on your hands and knees with a meter stick and you measured how far is it from the lab table to the target, you would have your dx. You've already calculated your t by figuring out the falling distance, and then you could accurately calculate the exit velocity of the dart that way. So that is how you will solve for the velocity of the dart as it exits the blowgun. It's just like problem 6. Okay, that is step 1. Step 2, I'm going to do in green, and it's fairly quick. If you think about it logically, the dart starts at a velocity of 0, you blow on it, and it exits with some high velocity, and typical velocities are between 20 and 30 meters per second for a blowgun dart. So there's an acceleration in the tube here, in the blowgun, because it starts at 0 and it ends at a high velocity, so there must be an acceleration here. Again, we don't have a stopwatch or anything to directly measure the acceleration, but we do have some physics and some formulas. We can measure the length of this blowgun with a meter stick. That's super easy to do. So now let's think about this. If you know the initial velocity is 0, you know whatever the final velocity is from the first part of the lab, you know the distance of the blowgun because you can directly measure it, and you're trying to figure out A, it's pretty obvious now which formula you're going to use. It's the VF squared formula. So you're going to say VF squared equals VI squared plus 2AD. Remember, we're trying to solve for A. So it's going to look like this. VF squared minus VI squared all over 2D equals A, and that is how you'll get the acceleration in the gun. I want to point out real quickly that the dart is only in this gun for a tiniest amount of time, and it goes really fast. So you would expect a very high value for acceleration. Typical accelerations for this lab are in the neighborhood of 300 to 500 meters per second squared, because it goes really fast. Okay. So this is how you'll get the acceleration in the gun. You don't even need the time that's in the gun. In fact, because we don't have a stopwatch, we only have a measurement device. So that is how you'll get your A value for inside the gun. Any questions on that, on the physics of this lab? Okay. What do we got for time?
A little under 9.
Ooh, perfect.